Hi there guys, this is 12E. This is an extension of your kinematics in vector format. So we'll be working out displacement vectors, velocity vectors, and acceleration vectors, all of which will have functions inside them which are dependent on time. And the difference with this exercise is we're extending the model to include exponential and trig functions inside the functions for displacement as well. Okay, so there's an investigation to start off with, this investigation 3, which I will go through at the end, because I know a lot of people will just simply want to have a go at example 4. Now, there's some competition here for doing the explanation video. You can always click on the link here, and there is a short 2-minute 30 explanation video offered by Oxford. You are welcome to go and have a look at that. But after I've gone through this as well, and I'll go through it quite quickly, I will go through investigation 3 at the end. Okay, so for example 4, let's have a look at this one. Just copied it across. I'm going to go through this fairly quickly. It says we have the displacement of r is this thing here. So we're based on cos, sine, but also inside here we can see we've got the exponential function there as well, e to the 0.5t inside there. Okay, so it says find the position vector of the particle when t is 0, pi over 2, pi, 3 pi over 2, and 2 pi. Well, the neat thing about choosing these, so 90 degrees or 180 or 270, that of course either sine, let's try and do a better version of that, either sine is going to be equal to 0 at 0, pi and 2 pi, or cosine is going to be equal to 0, and that's at this pi over 2 and at 3 pi over 2 there as well. So you can see why they've chosen these things. And of course, we've not got any transformation on cos or sine in these cases as well. So we're simply going to get zeros out for one or the other in each of these cases. So this is pretty straightforward. You can substitute 0 in here. And obviously, if you put 0 into here, you're going to get cos of 0 is equal to 1. And then you're just going to get out 10 in this case, because e to the power of 0 is going to be 1 as well. So that's going to give you your 10. And of course, you put 0 into here, and you'll get sine of 0 is equal to 1. So the whole thing is going to become 0. Okay, now you can find the other values on your calculator. Obviously, make sure that you're set up in radians. So that's pretty straightforward. We get the coordinates, and then we can plot these points on a coordinate grid, and you can see that we're starting here, and we're kind of spiraling inwards here. Now, obviously, we're just joining those points up, but if you chose, say, for example, pi over 4, you would expect that that wouldn't exactly be on here, and I would expect that it's somewhere around here to make this kind of smoother spiral. Okay, so describe the long-term behavior of the particle. Well, you can see that it is spiraling in towards 0. So that will be sorted out there. And then it says find the velocity of the particle at time t. So this is where it gets algebraically a bit more complicated, because you're going to need to differentiate this, and you're going to need to differentiate this. Now, both of those are a product of two functions there. So let's just get rid of everything on the page. So let's just deal with the x part here. And remember, of course, r is really equal to your position vector xy. So x in this case is going to be equal to 10, and we've got e to the minus 0.5 t, and times by cos t. So if we want to find the derivative of this, and the derivative will need to be in terms of t, because this is in terms of t, so we're now looking for dx dt, then we can use the product rule. So that's a uv, and the product rule here are dx dt, going to give us uv dash plus u dash v, and that's differentiated in terms of t with respect to t there in each of those cases. So what do we choose to be u? Do we choose the whole of this thing, or do we just choose this? Now, we could leave the 10 out and differentiate this and then multiply everything by 10 at the end. Maybe that's easier, but I think most people would probably just take the t and incorporate it in that first function there. So it's worth writing down to the side what u is and what t and what v is. I'm just going to save a bit of time here though, just to say that u dash, of course, is going to be just e to the minus 0.5t, but then of course times by the derivative of what's inside, because we have a function inside a function there. So we're going to get minus 5 in front there for u dash, and then for v dash here we're going to get minus sine t. So that's just using one of our standard rules. Okay, so when we put those ones together, we can now see we've got u v dash, so we've got n e to the minus 0.5 t times by v dash, so we've got sine t at the end, the minus on the front there, squeeze that in there, and then we've got this part as well, so u dash v, so we've got u dash, which is this, so minus 5e to the minus 0.5 t, and then multiplied by v, and v is just cos t. So that's cos t. Now that's going to be in the top line, your v. So this entire expression here is going to be here, and you'll need to do something similar for this one. Put it in there as well. So you'll need to differentiate that using the product rule as well. Okay, so obviously that's quite involved. And algebraically involved, and find the velocity of the particle at time t. We're done. We can write that as a velocity vector. It's not asking us to find the speed, in which case we'd need to work out the magnitude of the velocity, which would be quite tricky because it would be in terms of t. So we can just leave it as the velocity vector. That's no problem. Okay, and for part D, it says find the magnitude and direction of the velocity when t is 0. Okay, so obviously put t is equal to 0 into this, you'll get out a number, and put t is equal to 0 to whatever expression you get out here, and then you'll get a number there as well. And when you want to find the magnitude, that's just applying Pythagoras to a vector, and the direction, obviously, if you've got your vector like this, then if you split it into its component parts, say this is 5 and this is 10, then you can use tan 5 divided by 10, so tan to the minus 1 of that, in order to work out the angle. Okay, let's just check that in the book. So let's see what they've done. So you can see that they've actually factorized in part C for the second line there. So they've kind of skipped a lot of algebraic working out, but then they factorized. And let's just check what I've got in that first line. So I've got minus 10 e to the minus 0.5 t sine t. And that's what they put actually in the second part here. And then they've just swapped the order. And they factorized out in both cases. They can see that we've got e to the minus 0.5 t involved in both of those expressions. And they factorized out a minus 5 as well. So that's just making it a little neater in this case. And actually makes this pretty simple to work out from here. And then we get a minus 510. And then obviously magnitude is just Pythagoras applied to this. So minus 5 squared plus 10 squared, all square rooted. And the direction, we just do the direction. We've got minus 510 there. So we've got, so from the center, we've got 5 backwards and 10 upwards. So we're trying to find the direction of this. So if we use 10 and 5 there, we can work out this angle here. But the direction we're going to need from the positive x direction. So we're going to need to find this angle here. So whatever angle you get here, you can take away from 180 degrees. So that's all 5 backwards there. Okay, so let's have a look at the investigation. So this is a little extension here. The investigations in this chapter are really important, in fact, because there's a lot of working out which is going on in here in these investigations, and later on too, there's a lot of explanations of the maths which you essentially need to find yourself, and you can't find the worked investigations, as far as I'm aware, from the book. So you have to do these yourselves, and sometimes they're not that easy to go between the steps as well. Okay, this one, on the other hand, is relatively straightforward, so let's have a look at it. So investigation 3, and it says, consider a particle moving so that its position at time t is given by this equation here, where r and omega are constant values. Okay, so we have a trig function in the x part, the coordinate here of the displacement vector, and we have trig function in the y part, so no exponential parts here at all. Now it says, by considering the distance of the particle to the origin at time t, so distance, not displacement, distance is the magnitude of this, then show that the path follows the particle followed by the particle, is a circle centered at the origin and state its radius. Okay, so let's work with this then. So we've got the magnitude r here, and that's going to be r squared cos squared omega t. So that's me just squaring the whole of this. And again, as ever, just bringing the squared on the inside to both of those things. Okay, and then plus r squared sine squared omega t as well. Now, I need to square root that, but let's just write squared up there for the time being. Makes it a little easier to write down. Okay, and well, we can now see that in fact this thing here is x squared, and this thing here is y squared, and this is essentially the formula for the equation of a circle. So we've basically done that. So we can see that this thing is x squared, this thing y squared. So we've got our displacement squared, or our distance squared, which is r squared in this case, is equal to this, which is essentially is our distance. So so in terms of your normal equation of a circle, we are done. This is a constant here being squared. In terms of the distance at any given particular point, and that's equal to x squared y squared. So when I say at any given point, I mean any given time. Okay, so that is the equation of a circle. You can verify as well that r squared is popping out here as the size of this thing, because you can say as the distance essentially at any particular point, or the square of the distance, because we can factorize out r squared here, and we've got cos squared w omega t plus sine squared omega t. And remember, of course, that cos squared sine squared with some variable in the center is always going to be equal to 1. So this gives us r squared. So we've shown, like obviously really, that the displacement squared, or the distance squared, is r squared. So in other words, the distance is just simply r in this case. So we have a radius of r, so there's the distance of our circle, and we have x squared and y squared there. So that's in the format that's required. Okay, now I've gone and made this up. So I've just created this thing. And again, I've come up with my vector, but in a coordinate form on Desmos here. And if I press play on this one, so if I press play on the time, because time is the thing which is changing here, if I press play on this, you can see that we've got this point moving around in a circle. Okay, it's going backwards and forwards because I've just restricted this, the t to be between -10 and 10 is bouncing forwards. And obviously if I change that up and I just went from, let's say, 0 to, let's say, 2 pi, okay, and then if I press play on that, so starting at 0, that's my starting point, and if I go around here to 2 pi, there we go, at 2 pi, roughly so. See if I can take that one up there. No, I can't. So at 2 pi, there we go. You can see that it's gone back to the start. And obviously if I change that to 4 pi, so let's put 4 pi in here, we can then see that we'll get 2 rotations. So let's watch this one go around. So it's going to go around once, and it's going to go around twice in 4 pi. Okay, so there you go. So that's t. Obviously, I've kept a as 1 there, but if I wanted to keep a, and I've changed b there as well, put a b for a particular reason, so I'm going to go to that in a second. And so if a essentially is 2 in both of these cases, then you can see that I now have, oh, speed is going twice as fast. Okay, so that's increasing the frequency here. And if I change my radius, which is actually what I was thinking about, but there you go. So if I change my radius, you can see that I get a smaller circle. Okay, so there's my radius there. Now, the reason why I put A and B there is just to show you that we can come up with some pretty interesting stuff here. So if I bring this down to say 0.1 and press play on that, you can see that this thing is going in a kind of helix. It's just kind of interesting. Let's put that up to 1 again. So it's moving in a kind of helix pattern. Again, if I change t, I change this one here and I go down to, let's go down to minus 4 pi and press play on this one here as well. You can see it's going to go underneath the x-axis here as well. Okay, so it's kind of helix pattern going on. So it's kind of interesting. You know, you can bump that up to 1 and you can play around with putting a different r on there as well. You know, maybe let's put on s. And let's see what happens if we make s equal to 1.5. And so in this case, and then let's press play on t. Okay, so we need to slow that one down a bit. So, and zoom out, and you can see that this one is now going in an elliptical orbit, which is kind of interesting. Okay, right. So there you go. So anyway, we're back to this one. So if we have a look at the next few questions, let's just take these ones here and take 2 to 4 here. Okay. So again, it says write down the initial position vector of the particle. Well, the initial position vector, I think we've already got, in fact. The initial position vector was given, I think. Initial position vector is just using this. Sorry, it's not given because that's in terms of t. So this one is going to be r is equal to r cos 0. So omega t is going to be 0 there. And then we're getting r sine of 0 as well. And so that's going to give us, of course, this is going to give us 0. And this is going to give us 1 here, 1 times by r. So that's just going to give us r is equal to r0. And we can call that the initial point. We can say that's r0. So that's r and 0. This is coincidental, they're both the same. Okay, so that's our initial position vector in this case. Let's just write down r as well. So we've got it here, omega t, and this is r sine of omega t there as well. Okay, you can put brackets around these, but it's kind of understood there already. It's one thing there. Okay, so then it says find the velocity vector. So the velocity vector is not going to be hard here. So velocity is obviously just these two things differentiated. So we're going to get, you're going to need to apply the chain rule here. We're differentiating with respect to t, of course, because velocity is change in displacement over time, or with respect to time. So this is a function of a function inside, so we'll also need to times by the derivative of the function inside using the chain rule. So we'll get here minus r omega sine omega t, and we're going to get the similarly for this one here, we'll get rw, or omega rather, sorry, and omega t there as well. So that's just differentiating cos. And of course, this is not the product rule here that we're using. This is not a function of t. This is just a constant. Okay, so there's v. That one's done. So that's the velocity at time t. So then show that the speed of the particle is constant and state its value. So speed requires us to work out the magnitude of the velocity. And again, if you do this, you're going to get this thing squared. which is going to be this thing here squared. Room a little bit here. So this thing squared. I've got the minus in there, but obviously when you times a minus by a minus, it becomes positive. Times by sine squared omega t, and then also plus r omega cos omega t squared. Now, if you factorize out this, you're obviously going to get sine squared and cos squared left in there, which is going to be equal to 1. So you'll just end up with r omega squared. And I've forgotten something here because I've forgotten that I did not square root things. So that's the speed squared, if you like. So that's the speed squared. And then if we want this, just the speed itself, it just gives us r omega. Okay, so that's good. Right, and we've shown that it's constant state and stated its value. It's constant because these two things are constant here. These are not functions of t. So show the velocity is always perpendicular to the particle's displacement vector. Okay, so the displacement vectors are always in a circle centered around 0, 0. And when they're talking about the velocity always being perpendicular, they mean at any particular point here, the velocity is moving, well, one way or the other way. It's going in this direction, I think. So, but this is always going to be at right angles. Wherever we're moving, we're trying this object is moving at right angles in its orbit, at right angles to that radius essentially. So show that the velocity is always perpendicular to particle displacement vector. Now, I think there's a couple of ways of doing this. You could work out the gradient. Let's do the gradient of r, and that's going to be your r sine omega t divided by, so change in height divided by change in distance across. That's r cos omega t. So that's going to be the gradient of r. And then the gradient of v, so mv, is going to be equal to this over this. So we can see that we're getting there cos omega t by r omega, and then r omega sine omega t there. And so that's a gradient. Okay, so that's just change in y divided by change in distance across. And then we could cancel these two things here, cancel these two things here. And you could see that this one is going to end up still being negative. And so when you times those two things together, you'll get m, the gradient of r times the gradient of v is equal to -1. Okay, well, that's one way of doing things, but seeing as we're dealing with things in terms of vectors, perhaps it's better to do r underlined, so the vector, the displacement vector, dotted with v, your velocity vector, and show that that's equal to 0. That shows us that we have, remember the formula, of course, we have this times cos of theta. So this is your dot product or your scalar product. And when you have 90 degrees in this, you'll get cos of 90 is equal to 0. So the whole of this side will be equal to 0. So if you can show this, the dot there, not a 1, then we also have shown that we have 90 degrees between them. Okay, so let's just take that back. Okay, and I think probably it's better to use the dot product in this case. I'm not going to do that one now because I've already shown you another way. So there we go, that one's done. And then explain what this means geometrically. Well, we talked about this. It means that the velocity is always at right angles to the radius or the distance to the center. Okay, so find the acceleration of the particle at time t. So obviously now we need to do velocity differentiated. So this one differentiated. So now that's going to be acceleration is equal to, now we differentiate this thing here, and we'll get, so again, we're going to differentiate this. This is just a constant outside the front, and we'll need to use the chain rule again with this. So that will give us minus r omega cos omega t, And then underneath, we're going to get minus r omega sine omega t. And there we go. That's that one done. Find the acceleration of the particle at time t, and then show the acceleration is always perpendicular to the velocity vector. So again, we've got the choice of ways in which to do this. Perhaps let's do the dot product this time. So if we do v dot a, we can see that we're getting this times by this, which is going to give us, just thinking about this one, I think slightly wrong here, right? It's a mistake here. Forgot to times by omega, by the chain rule essentially. So there's an omega squared there, in fact. Okay, so v times by a, so vector of v times by the, or dotted with the vector of a, gives us these two things at the top multiplied together. So we're now getting r squared w cubed, and then we're getting sine squared omega t, and then sine omega t, and then cos omega t. And that's this one times by this one here, and then that's plus, and then we've got this times by this. So in this case, we've got r omega cubed, and then we've got cos omega t sine omega t. And I've made a mistake again. You can see two mistakes there. In fact, there's a sine r squared there, and this shouldn't be a plus. This should be a minus. You can see that's a positive times by a negative there. Right, okay, that's the problem with having such messy working out. Okay, so now you can see that this takes away from this, and that leaves you with 0. So that's a nice way of showing that the two things are perpendicular. So therefore, we can say that these two things are at right angles to each other. Okay, good. So finally, it says show the acceleration is always perpendicular. We've done that. That's kind of interesting, by the way, in that the velocity is always perpendicular to the displacement. So this will be your velocity, but your acceleration, which here is going to be going to be going in. Let's check on that one. Put that one right here. So that's going to be trying to accelerate again in this direction here. So it's either accelerating towards the center or away from the center there, but it's accelerating in this kind of direction here. Right, which I can't remember what that's called now. Centrifugal force, I think. Okay, so that's the acceleration due to this centrifugal force. Okay, right, and we've done that, and then let A be the acceleration, the vector of the particle. Show this, so simply going to part C, we're going to take the magnitude of A, so magnitude of A, and again, running out of space a little bit here, but if you square this, and if you square this and add them together, you'll get A squared, and then you can factorize out this thing squared and this thing squared, and you'll be left with cos squared and sine squared again, which will become 1. So you'll end up getting r squared r to the power of 4 there when you square this and this. So that's just using Pythagoras with this. And so that's your magnitude of A. Now remember that the magnitude of V is RW, and they're trying to say that that's V squared. So V squared would be this thing squared. So that would be R squared W squared. So that would be V squared. Where am I going with this one? Well, I've forgotten to do something, haven't I? I've forgotten to, that's the magnitude of the acceleration squared. So that acceleration is actually RW squared. And RW squared, we could say, is the same as doing RW all squared divided by R. There we go. And then we've got V, which is over here squared and then divided by r, and that's proving this thing here. Right, so there's one last little bit, and I can't squeeze it on easily, but I think this one is actually quite straightforward. This is saying show that your acceleration vector is equal to k times by your displacement vector. Well, have a look at this. Look at this. You can see that this one is the same as this one, but we're timesing by minus w squared or minus omega squared there. Okay, so you can see quite easily for that last one that we've got a is equal to minus w's omega squared times by your displacement vector. Okay, so k is equal to minus omega squared. Okay, well, I'll be amazed if anyone got through all of that one, but there you go. There's the investigation in full. There's a final part of this which I don't quite get really. It says, how would you derive the velocity and acceleration equations for the particle moving a circle from the general equation for its displacement? I think we've kind of done that actually. So we started with the general equation for its displacement here. So I'm not quite sure what they're talking about there. I think I misunderstood their question, but I think we've kind of done that. Okay, then guys, well, you've got now 12E. It's a relatively straightforward exercise. There are 6 questions. Good luck with those. The next section is going to get hard again. So enjoy it while it lasts.